Now we are going to do an important derivation of magnetic field due to a uniformly magnetized matter. So now you have a uniformly magnetized material, and for that we will find out the relation of the magnetization. Now let's say you have a sample, a magnetic material. Now this material has a certain thickness. Now this is a three-dimensional picture, so you have to imagine that this is the upper surface and this yellow portion, this is the thickness of the material. So this whole sample will have a certain thickness, and let's say that thickness is dy. So let's say this thickness over here, this is dy. So it has uniform thickness all around the sample. Now this material has been magnetized using external magnetic field. So let's say if you apply magnetic field in the upward direction, then if this material is paramagnetic substance, then this substance will get magnetized in the same direction as that of the magnetic field. Means if the external magnetic field is in the upward direction, then this material will get magnetized in the upward direction, and if it is diamagnetic substance, then this material will get magnetized in the downward direction. So just take that this material has got magnetized in the upward direction. So no matter what is the direction of the magnetic field, the external magnetic field, let's say that this material has got magnetized in the upward direction. Now I have divided this material into large number of magnetic dipoles. So you can see here large number of squares which are drawn. So these represent one magnetic dipole. So every square represent one single magnetic dipole. Now let's say the magnetic dipole moment of every magnetic dipole is represented by mu m vector. As we have said that this material gets magnetized when it is placed in magnetic field. So this material has got magnetized. So what is the magnetic dipole moment of every magnetic dipole? That is represented by mu m vector. So let's take this particular magnetic dipole. Now the magnetic moment of this magnetic dipole will be in the upward direction, and that is represented by mu m vector. And this material is made up of large number of atoms or molecules, and we have said already that these atoms or molecules, they have their magnetic dipole moment. If it is a paramagnetic substance, so it will have magnetic dipole moment, and that arises due to L vector and S vector. So electrons in atoms or molecules, they orbit as well as they spin on their own axis. So due to orbital angular momentum and spin angular momentum, there is production of magnetic dipole moment. So when a substance is magnetized, all these magnetic dipole moments get oriented in the same direction. So all the magnetic dipoles will be in the same direction. So if the magnetic field is applied in the upward direction, then all the magnetic dipoles will get aligned in the upward direction. And if the magnetic field is in the same direction, in the upward direction, and if it is a diamagnetic substance, then the magnetic dipoles, all the magnetic dipoles will get aligned in the downward direction. So all the dipoles, they are oriented in the same direction. Now every magnetic dipole moment is represented by mu m vector. So each atomic dipole has magnetic dipole moment is equal to mu m vector. So over here, every square represents one magnetic dipole. And let's say there are n dipoles in unit volume. So if you take a unit volume of this sample, let's suppose there are n number of dipoles in unit volume. So what will be m vector? Now m vector is the magnetization. So this is the magnetic dipole moment in unit volume. So there are n dipoles in unit volume, and magnetic dipole moment of each atomic dipole is represented by mu m vector. So m vector can be written as number of dipoles in unit volume times the magnetic dipole moment of each atomic dipole. So this will be equal to magnetization, means magnetic dipole moment in unit volume. Now as we have said that thickness of this material is equal to dy, and every atomic dipole is represented by a square. So let's suppose that this area over here, this area is equal to dA. So this small area of each atomic dipole is equal to dA. So dA is the area of each dipole and dy is the thickness of the material. So dy is the thickness. So let's say this is equal to dy. So this is the thickness of the material. So what will be the volume shared by each dipole? So each dipole has area equal to dA and there is a thickness of dy below this surface. So this is a three-dimensional picture. So there is a thickness of dy below this whole surface. So what will be the volume shared by each dipole? So volume is equal to area times the thickness. So volume shared will be equal to dA into dy. Now magnetic dipole moment of each atomic dipole. So if this is one atomic dipole, so magnetic dipole moment mu m vector, this can be written in terms of current. As we have seen in the previous lectures that magnetic dipole moment is due to the flow of current. So in this magnetic dipole, let's say the current is flowing in anti-clockwise direction, means in this manner. So current is flowing in anti-clockwise direction and due to that the magnetic dipole moment is in the upward direction. Let's say I is the amount of current which is flowing in this atomic dipole. So I is the amount of current. So mu m, which is the magnetic dipole moment of each dipole. So mu m can be written as current times the area enclosed. Now what is the area enclosed? That is equal to dA. So I is the current flowing in the anti-clockwise direction times dA will give you the magnitude of the magnetic dipole moment. So mu m can be written as I times dA. Now the magnetic dipole moment can also be written in terms of magnetization. As we know, magnetization m vector, magnetization is the magnetic dipole moment in unit volume. Mu m is the magnetic dipole moment of each atomic dipole. As we have said that volume shared by each dipole is dA into dy. So this is the volume shared by one atomic dipole. So mu m is the magnetic dipole moment of one atomic dipole and volume shared by this magnetic dipole is dA into dy. So mu m can be written as m, which is the magnetic dipole moment in unit volume, times the volume shared by each dipole. So this will give you the magnetic dipole moment of each magnetic dipole. So m is the magnetization. This is the magnetic dipole moment in unit volume. So magnetic dipole moment in unit volume times the volume of each magnetic dipole will give you the magnetic dipole moment of each atomic dipole. So mu m is equal to m into dA into dy and mu m is also equal to I into dA. So this can be put equal to I into dA. Now dA will cancel with this and you will have m into dy is equal to I. So I is the current which is flowing for the case of a single atomic dipole. Now from here you can write m is equal to I divided by dy. Now if you will look at one atomic dipole, so let's say you take a single atomic dipole. Now in this case we have said that this material has got magnetized in the upward direction. So capital M vector capital M vector, which is the intensity of magnetization, this is pointing in the upward direction. And magnetization in the upward direction will arise due to the flow of current in the anti-clockwise direction. So current will flow in anti-clockwise direction in this atomic dipole. Then in this atomic dipole, the current will flow in anti-clockwise direction. Similarly, in this third atomic dipole, the current will flow in anti-clockwise direction. So in all these atomic dipoles, the current will flow in anti-clockwise direction. Only then the material will get magnetized in the upward direction. So if you will take this atomic dipole, so if in this case the current is flowing in anti-clockwise direction, means in this manner the current is flowing in anti-clockwise direction. Now if you will take the neighboring dipole, if you will take into account, now in this atomic dipole the current will flow in anti-clockwise as well. So current will flow in this manner. Now you will see that at this boundary the current will cancel with each other. So you can see at this boundary the current was flowing in upward direction due to this dipole. Now due to this dipole, the current at this same boundary is flowing in the downward direction. As we have said that this material is uniformly magnetized, means current in each dipole is the same. So current in this dipole, the magnitude of current is same as that of the current flowing in this dipole, is same as that of the current flowing in this direction, in this dipole. So at this boundary you can see that current is flowing in upward direction as well as in the downward direction. So these two values of current will cancel with each other, and hence at this boundary current will be equal to 0. So the same case can be seen for the case of third atomic dipole. So in this case current will flow in anti-clockwise direction. So current will flow like this. So at this boundary you will see that current will flow in downward direction due to this third dipole, and earlier the current was flowing in the upward direction due to this second dipole. So current will cancel at this boundary also. And similarly, if you will take this atomic dipole, you will see that current will cancel at this boundary. So current in this dipole will flow in anti-clockwise direction. So you can see that at this boundary currents are in the opposite direction. So you can clearly see that current at all these boundaries, at this boundary, at this boundary, at this boundary, at this boundary, at all these boundaries current will be equal to 0. So the only current which is left is the current at the boundary of this material. So if you will take this atomic dipole into account, you will see that current will cancel at this boundary due to this dipole. Similarly, current will cancel at this boundary due to this dipole. So only current which will be left will be on the boundary of the material. So current will be in the anti-clockwise direction. So at this boundary as well as at this boundary the current will cancel due to the neighboring dipole which is present, and the only current which is left is the current at the boundary of the material. Similarly, the current will be left at this boundary. Similarly, the current will be left at this boundary, and so on. So at the boundaries where you have a neighboring dipole, at all those boundaries the current will cancel, the current will be equal to 0, means inside the material there will be no bound current. The only current which you will have will be at the boundary of the whole material. So inside, at every boundary current will be equal to 0. So you will only have the current at the boundary of this magnetic material. Means the current is flowing at the boundary like this. So current is flowing at the boundary. So this is the boundary, ribbon shaped boundary. So current is flowing in the anti-clockwise direction. So there will be net current flowing only at the boundary of the magnetic material in the anti-clockwise direction. Now over here, what will be current? Current will be equal to capital I. So I amount of current is flowing. Now in this case, if you will take into account the thickness, so the current is flowing along the thickness of the material. Now what is the thickness? This much thickness is equal to dy. So amount of current which is crossing this thickness is equal to I. So thickness is dy and the current crossing this thickness is equal to capital I. So current is only flowing at the surface. So you can clearly see that current is flowing only at the surface of this material. So I divide by dy will give you the surface current density. So there is no current flowing inside the material. So inside the volume of the material, current is equal to 0. The current is just flowing on the boundary, and this is a three-dimensional picture. So this has a certain thickness which is equal to dy. So current is flowing along the thickness of the material only. So thickness is equal to dy and amount of current crossing the thickness is equal to I. So what will be I divided by dy? That will be equal to surface current density. So I divided by dy is equal to surface current density, and that is represented by Js. So from here you will get Js is equal to capital M. So when the material is uniformly magnetized, current inside the material is equal to 0. And the surface current density of a uniformly magnetized material is equal to the intensity of magnetization. So this is the formula which we have derived for the case of uniformly magnetized material. Now in the next lecture we will look at the case of non-uniformly magnetized material. So if you have a non-uniformly magnetized material, so current will not be the same in all the atomic dipoles, and due to that there will be non-zero current inside the volume of the sample. So in the case of uniformly magnetized material, you have zero current inside the volume, and the only current which is flowing is at the surface, at the boundary of the material. But in the case of non-uniformly magnetized material, you will see that current is non-zero inside the sample. So that is the difference that we will see in the next lecture.